All right, let's dive in. We're about to pull back the curtain on a hidden pattern that, believe it or not, describes a huge part of the world all around us. We're talking about everything from how tall people are to test scores. There's this secret shape that brings a kind of order to what looks like total chaos. So let's go find it.
To get us started, I've got a little riddle for you. What on earth could possibly connect the salary of a teacher, measured in dollars, with how long a calculator is expected to last, measured in months? I mean, they seem totally random, completely unrelated. But they're not. They actually share a really powerful secret.
And the answer is this shape, this really elegant, simple curve. You've definitely seen it before, right? It's called the bell curve, or if you want to get formal about it, the normal distribution. And I'm not exaggerating when I say it's one of the most important ideas in all of statistics.
So let's get properly introduced. What is this thing really? And where else can we find it hiding out in plain sight? Okay, so the normal distribution isn't just some abstract drawing. It's a super powerful tool. The official term is a continuous probability distribution, which I know sounds complicated, but it's just a way of saying it helps us make sense of things that can have any value in a range, like height or weight, not just a few fixed numbers. And it is absolutely essential for modeling tons of real-world situations.
So what gives this curve its famous shape? Well, it all boils down to a few key properties. First, it's perfectly symmetrical. The left side is a perfect mirror image of the right. Because of that, the average, the middle value, and the most common value are all the exact same number, right there at the center. It's also got just one peak. We call that unimodal. And here's the kicker. The total area under the entire curve always adds up to 1, or 100%. That's going to be super important later.
Now here's the thing, not all bell curves look exactly alike. You can have tall, skinny ones, short, wide ones, and their specific shape and where they sit on the graph, that's all controlled by just two key settings. Let's break them down.
These two settings are the mean and the standard deviation. The mean is basically the anchor. It tells you where the center of the curve is, where that peak is located. The standard deviation, on the other hand, is all about the spread. It tells you how stretched out or squeezed together the data is.
Check this out. Here you can see exactly what the mean does. We've got two curves here with the exact same shape, the same spread, but see how one is just shifted over to the right? That's because it has a different mean. You can think of the mean as the address, telling you exactly where the center of your data lives.
Okay, now let's see what happens when we play with that other knob, the standard deviation. This time, both curves have the same mean. See how they're centered on the exact same spot? But their shapes are totally different. The tall, skinny curve has a smaller standard deviation. That means the data is all packed in really tightly around the average. The shorter, wider curve is more spread out, more varied.
And this leads us to a really practical problem. Okay, so teacher salaries have their own mean and spread, and calculator lifespans have their own mean and spread. So how in the world can we compare them? It's like comparing apples and oranges, right? What we need is some kind of universal translator.
And guess what? We have one. It's called the standard normal distribution. This is our universal benchmark, our common ground. It's a very special bell curve that is always centered at a mean of 0 with a standard deviation of 1. By converting all our different data to fit this one standard curve, we can suddenly compare anything to anything.
And the magic tool we use to do this conversion is called a z-score. The absolute best way to think about it is like a standardized ruler. It's a ruler that lets you measure anything, salaries, lifespans, test scores, you name it, on the exact same scale.
So what is a z-score actually telling you? It's surprisingly simple. It's just the number of standard deviations a particular data point is away from the average. So a positive z-score just means your value is above average. A negative one means it's below average. And the formula to figure it out is beautiful. You just take your value, subtract the mean, and divide the whole thing by the standard deviation. That's it.
All right, enough theory. That was the setup. Now let's put this whole toolkit to work and actually solve a real-world problem using what we just learned. This is where it gets fun.
Okay, here is our problem. We know from our research that U.S. teacher salaries follow a normal distribution. The average, or mean, is $51,000, and the standard deviation is $6,000. So the question is, what are the odds? What's the probability that if we pick one teacher at random, they earn somewhere between $42,000 and $65,000? We've got a clear two-step mission ahead of us. First, We're going to take our two salary numbers, 42K and 65K, and use our standardized ruler to convert them into z-scores. Then, for step 2, we just need to find the area under that standard bell curve that's between those two z-scores. That area, that's our probability.
Let's do step 1. For $42,000, we do the math, and we get a z-score of -1.5. That tells us that salary is 1.5 standard deviations below the average. Then for $65,000, we get a z-score of positive 2.33. So that salary is over 2 standard deviations above the average. Easy enough.
And now we can actually see what we're looking for. We've put our two z-scores on the standard curve. There's -1.5 on the left and plus 2.33 on the right. That shaded area trapped between them, that little slice of the curve, that is the probability we're looking for.
And when you look that area up in a z-table or use a calculator, boom, there's our answer, 92.33%. That means there's a 92.33% chance that a randomly selected teacher in the U.S. makes between $42,000 and $65,000 a year. See, we just took a messy, real-world question, translated into a standard language, and got a concrete, useful answer.
Now, solving one problem is great, but the real magic of the normal distribution is just how useful it is for, well, almost everything. So let's zoom out and look at the big picture for a second.
Think of the bell curve as a prediction engine. A company can use it to figure out how many of its calculators are likely to break while they're still under warranty. An IT department can predict the odds that a computer repair will be done by 5 o'clock. A factory manager can check if a machine is still working properly after it's been serviced. These are all wildly different questions, but they're all answered using the exact same logic we just walked through.
And like one of our sources says so clearly, its power really lies in its ability to model a vast number of situations that just happen naturally out in the world.
And really, that's the whole point. This one simple shape is like a special pair of glasses that helps us make sense of the world. It lets us understand why things vary, it lets us measure risk and make smart predictions, and most importantly, it helps us find order and patterns where it might otherwise just look like a bunch of random, chaotic data.
So I'll just leave you with this question. Now that you know the secret, now that you know what to look for, start paying attention. You'll see it in sports statistics, in the stock market, even in nature. Where else will you spot the bell curve shaping the world around you?